Hello everyone, welcome to the tutorial about CMake. So first, let's see what is CMake. CMake is used to control the software compilation process. Remember, in Visual Studio, we can press the green triangle to run a project, right? And with CMake, we can write a file to run the project. CMake is a flexible cross-platform tool. We can write the configuration file once and run the projects on different platforms like Windows, Mac, and Linux. CMake is also used in lots of open source projects, so learning it also helps us to understand others' projects. There are other choices to build a project. For example, we can write Makefile and use Make. We can also use the command line tools like GCC and G++. But when there are too many source files, using the commands or writing the Makefile can be very complicated. Then we can use CMake to generate the Makefile and then build the project. That means we don't need to write the Makefile by ourselves. In this tutorial, I will show you how to use CMake on Linux to build C project. It's almost the same for C++, but I just used C source code for demo. So first, let's install CMake in Linux. We can open a terminal and enter this command, sudo apt install CMake. And then we will see a lot of messages, and it asks you, do you want to continue? You can enter Y to continue and wait a few seconds. Then we can use this command, CMake -- version, to check the version. And if you can see the version, it means you have installed the CMake successfully. But notice that here the version is not the latest version, but it's already enough to use. If you want to get the latest version, you can go to the first link to download it and follow the guidelines in the second link to install it. Then let's see a simple example. We have a source file called helloworld.c, and it will print a line in the terminal. To use CMake, we also need another file called CMakeList.txt. We should use this name and do not change it. And we should write this file by ourselves. Writing it is also the most important part of using CMake. So now let me demo it in the virtual machine. So first, let's create a new folder to do the demo. Call it CMake and go to CMake. Now the folder is empty, so we need to create the files. First, let's create the source file. In the main function, we will print a line. Okay. And we need to create another file that is CMakeList.txt. When we run CMake, it will find this file and use the commands in it to build the system. So let's write the commands. The first command should be CMake minimum required. So this command specifies the lowest version of CMake that is required for this project. Let's see the version of our CMake. That -- version is 3.16. So we can require any version that is lower than 3.16. And here we use 3.4 because we should use the lowest version that we can so that other users with lower version can also run our project. But some features may require higher versions, But now we don't need to worry about that. So let's continue. The second command, we will specify the name of this project. Project and set any name. Then we will specify the source file used to generate the executable files. The first parameter, we should write the name of the executable file. Let's call it hello. And this hello don't need to be the same as our project name. You can set any name. And the second parameter, we will set the name of the source file, that is helloworld.c. Okay, now we have everything ready and we can build our project. So let's go back to the terminal and invoke CMake. We should have a second parameter, and this is a directory that contains the CMake list.txt file, and it's the current directory here. So we can see some messages. It invokes some compilers and do some configuration. Now let's see what we have in the current directory. So we can see that this CMake command didn't generate any executable file. And what it generated are some files and folder. They store some variables. For example, if we CMake again, it will look at these files so that some repeated work will not be done. Let's try to CMake again. You can see that there are fewer messages and it will not find the compilers again. So these files are not quite important for us now, but there's one important file, makefile. And actually what CMake is doing is to generate the makefile, and then we can use make to build the project. And make will find this makefile and use this makefile to build the project. Okay, we make successfully, and let's see what we have again. Okay, now we can see the executable file, and let's run it. It works fine. Notice that every time we use CMake, it will generate lots of files. If we change the code and want to build again, we need to clean all the temporary files carefully. And I don't want to delete the source files. So it is not very good, and we need a better way to manage the temporary files. Actually, what we just did was called in-source build. That means we run CMake in the folder that we place CMake lists.txt. Here we introduce another concept called binary directory. It is a directory that we run CMake command. And all the binary files generated by CMake will be stored in the binary directory. So in our example, the binary directory is the current directory, and it's the same as the source directory, which is the top-level directory of our project. And here we have all the binary files together with our source code. So a better way is to run CMake in another folder, so that the binary directory will be that folder, and the temporary files generated will be stored in that folder. Then we can delete them easily. To do that, we can create a new folder called build and go to that folder. We call it build because it's a convention. Then we run CMake again. But this time we cannot use one dot because we don't have the CMake list.txt here, and we should use two dots because the file is in the outer folder. Oh, sorry, we need to go to build first and CMake But now let's see, we don't have the files in this folder, so we need to delete the files here, because this file contains the information of our previous build, and we need to delete the temporary files. Okay, and we go to build again. And we CMake again. And let's see what we have in here. Okay, we have made the make file, and we can make again. Now we have the executable file and we run it. It works fine. Now we can remove the binary files easily. We can just remove everything in this folder. And then we can start again. There is another advantage of using out-of-source build. If your project is shared with others on GitHub, you don't want to push the temporary files to GitHub. Then you can just git ignore the build folder, and you don't need to worry about the executable files and the binary files when you push to GitHub. Let's have a look at the make file generated by CMake. First, we need to CMake again. We can see that it's very complicated, and usually we won't write makefile in this way. Then let me explain more about the CMake commands in the example. So the first command is specify the minimum required version of CMake. For example, my CMake is 3.16, so I can use 3.4 or 3.5. Then let's see the second command, project. It specifies the name of the project, but here we can specify more information besides the project name. For example, the version of your project. You can use keyword version and set the version number here. You can also specify the language used in your project. For example, in our example, we only have a C source file, so I can use the first command. But I can also use the second and the third command because we specify more languages, but we still have the C language. CXX means C++, and Java is Java. So here it actually specifies which compilers we used in the process. So if I have a C++ source file, I can only use the second and the third command, but I cannot use the first command because it doesn't involve the compiler for C++. If you want to specify the version and the language in one command, you can write like this, and we need to use the language keyword to specify the language. But if we only specify language, we can ignore this keyword like what we do in the last slide. In the third command, add executable, we can set the name of our executable file, and also the source files used to generate this executable file. In our example, we only have one source file, helloworld.c, but actually we may have more than one source file. So then let's see an example with more than one source file. Here we still want to print hello world in terminal, but we have two source files, main.c and hello.c. In main.c, we just call a function which is declared in hello.h. And this function is actually defined in hello.c. So we need to compile both of them to generate the executable file. And in CMake list.txt, we can add one more source file in add executable command, and then it will work. Let me demo it in the terminal again. In the virtual machine, I have prepared the files. Let's have a look at them. In main.c, I called a function which is declared in hello.h. And this function is actually defined in hello.c. So we need to compile both of hello.c and main.c to get the executable file. And now let's write the CMake list file. First, let's set the minimum required version of CMake. And then the project name. And finally, we add the executable file. We set the name of the executable file to be hello, and we will use main.c and hello.c to generate this executable file. We can directly add the hello.c after main.c. Okay, so now let's go to build the project. We use out of source, build, and CMake. Okay, and then make. We have the executable file, and let's run it. It works fine. Before stepping into another example, I want to introduce the variables in CMake. Like the other languages, CMake also have variables. We can use set to define a variable and give a value to it. The first parameter will be the name of the variable, and the second parameter will be the value that we want to set to the variable. So let's see some examples. The first command, we set a string 1 to the variable myMajor. In the second command, we set a string 2 to the variable myMinor. Notice that in CMake, variables are considered to be strings. So in the second command, even though we don't use the double quotes, we actually set the variable to be a string too. We can also use variables as the value of another variable. So we need to use a $sign and curly brackets before the variable. Let's see the third command. Here I use the value of the variable myMajor and also the value of myMinor to be the value of my project version 1. We can also use double quotes to code this string, and they will return the same result. Then let's see another command, message. It will print a message in the terminal. For example, you can print a variable using the $sign and the curly brackets. You can print the variable like this, and you can also print a string together with the variable. You can also print two variables, but the result will be one string. Remember, we defined my project version 1 to be myMajor.myMinor, and now we can see the result of it. It's 1.2, and the version 2 is also 1.2. So actually, these two commands are the same. Now let's see another example. We set a variable myPlatform to be Linux, and another variable Linux welcome message to be welcome to Linux. Notice that the Linux here is the same as the Linux here, so we can replace this Linux with this variable. So here, we want to print the variable Linux welcome message, but we replace the Linux with the variable myPlatform. And finally, it will become Linux welcome message. And we will see this message in the terminal. So the usage of variables is very flexible in CMake, and you may try more by yourself. With the help of variables, we can rewrite the CMake list file in example 2. Remember that in example 2, we use two source files, main.c and hello.c. And with the help of variable, we can set a variable srcs sources to be main.c and hello.c. Then we can just call this variable in add executable. But if there are too many source files in your directory, it's hard to add them one by one into CMake lists. So here we can use another command to collect the names of all the source files in the specific directory and stores the list in the variable provided. So here the example 2 again, we can rewrite it as this. We use this command to collect the names of all the source files in the current directory and stores them into a list sources srcs. Then we can use this variable in the add executable command. There are some variables that are defined and used by CMake. Here I list some frequently used CMake variables, and I will introduce them later when we use them. Then let's see example 4, using subdirectory. In the previous examples, we put the source file in the root directory, but usually we place the source files into a subdirectory instead of the root directory. So now let's see how to rewrite the CMake list files to deal with this situation. In this example, we will write two CMake list files, one in the root directory and one in the subdirectory. I have prepared the source file in the virtual machine, main.c in src. So first let's write the alter CMake list file. The version and the project name. If we use the commands before, we can write add executable and the name of the executable file and the path to the source file. So we can write this. src. But this time we are going to introduce another command, so we will not use add executable. But if we use add executable, they will have the same result. So we use add subdirectory. And the name of the directory you want to add, that is src. So this command, in this CMake list, we didn't add the executable file. Instead, we add a subdirectory. So CMake will go to this subdirectory and find the CMake list file there, and then execute the commands in it. So let's go to write another CMake list. Go to src and because we have write the version of CMake and the project name before, so we can directly add the executable file here. Because we are already in src, so we can just write main.c. Okay, and let's build the system. Go to build folder and CMake. Okay, and then make. Let's see what happened. Here in build folder, we didn't see the executable file, but we see a folder src. Let's go to src and see what happens. We can find the executable in this subdirectory. Let's run it. OK. Remember that we have two CMake list files, one in the root folder and one in src. So here the files generated by the outer CMake list will be stored in build because we called CMake in build. And the files generated by the inner CMake list will be stored in src. And that's why we can see the executable file in src. So what if we don't want to generate the files in src? We can change it this way. We go to the outer CMake list. And in this command add subdirectory, we can set the second parameter to be the path to store the output files. And let's see what happens. Remove the files and CMake. Then make. Now we can already see the folder bin. Go to bin and we can see the executable file in bin. So actually the src folder is replaced by bin. But now if we want to find the executable file, we need first go to build and then go to bin. So we can also change the path of the executable file. This time we go to src and change the CMake list here. So here we change the executable output path to this path. And this variable is the source directory of this project, and that is 4. And it will create a folder bin under CMake 4. So if we change this variable, we will only change the path of the executable file, but all the binary files will still be stored in bin. Let's go back and see. CMake. We still have the folder bin, and now let's make. Let's go to bin. But this time we don't have the executable file here. Instead, we have the executable file in this, in here. We can see in the root folder we have a folder bin. And this folder is generated just now. And go to bin. We can see the executable file here. Now we know how to generate executable files. But in real projects, we often write and generate libraries. So in this example, we will see how to build libraries. First, let's have a quick review on it. There are two kinds of libraries, static libraries and dynamic libraries. For static library, it will first generate the lib. Then the linker will copy the content in the lib into the executable file. So we don't need the static library at runtime. That means if we delete the static library, we can still run the executable file. In Linux and Mac, the name of static libraries is libsomething.a, and in Windows, the name is something.lib. For dynamic libraries, it also generates the lib first, but then the linker will not copy the content from the dynamic lib to the executable file. It just links them together. So we will need dynamic libraries when we run the executable file, and we cannot delete them. The name of dynamic libraries in Linux can be something.so or something.so and the version number of this library. In Mac, it can be something.dylib, and in Windows, it can be something.dll. In CMake, we can use add library to generate libraries. The first parameter is the name of the library. Then we can specify the type of this library to be static, shared, or module. Here shared means dynamic library. Then we can write the source files to build the library. For example, the first command will generate a library called mylib1, and the source files to generate it are source1.c and source2.c. Here we didn't specify the type of this library, so by default, it will generate a static library, and mylib1 is static. The second command and the third command, we specify the type of the library. It's static and dynamic library. But there is a command. We can use this command to generate shared libraries for the commands that we did not specify the type of the lib. So if we use this command when we run CMake, the first command will generate a dynamic library instead of a static library. But the second command will still generate a static library, and the third command will also generate a dynamic library as before. Now we have built the libraries, but we still need to link the libraries to the executable files. We can use this command, target link libraries. The first command is the name of the executable file. The second command is the name of the libraries to be linked. Let's see the examples. In the first command, we will link the library mylib1 to the executable file hello. In the second command, we will link the two libraries mylib1 and mylib2 to the executable file hello. Now let's see an example. We use the same source code as example 2. In the main program, we include the header file hello.h and call the function in it to print hello world. As we know how to add subdirectories, we can restructure the project. We can put the source files into src and the header file into include. We also have two CMake lists, one in the source directory and one in the subdirectory. The outer CMake list is easy to write. The version of CMake, the project name, and add the subdirectory. In the inner CMake list, we first build the library by add library. HelloLib is the name of the lib, and we use hello.c to build it. Then we add the executable file, hello, with main.c. Remember, in the main program, we include a header file, so the compiler should be able to find the header file. But now, we put the header files in another folder include, and compiler doesn't know it now. Therefore, we should tell the compiler about the directory using include directories. And this given directory will be added to the search lists of the compiler so that the compiler can find the header files. Here the project source directory is where we last called the project command, and it's in the outer folder, the outer CMake list. So the project source directory refers to this current directory. And then we go to the include folder. So finally, we link the executable file hello with the library hello lib and finish the CMake list. Now let's build the project. I have prepared all the files, so let's go to Build and CMake. The make. Okay, we go to the subdirectory. Here we can see the executable file hello and a static library lib.hello-lib.a, and it automatically adds a lib before our name. So now here we have a static library. How to generate a dynamic library? There are two ways. And the first way is to change the CMake lists in the inner folder. Here, we didn't specify the type of the library in add library, and by default, it is static library. So of course, we can specify the type, like static or shared. And this is very simple, so I want to show you another way. And that is change the parameters in CMake. So we go to Build, and first remove everything. Then we CMake again, but here we will set another parameter. Debut shared libs equals to on, then dot dot, and make. Go to the subdirectory. Here we can see the executable file and a dynamic library ended with .so, and it also adds a lib before our name. To further restructure our project, we add new folders bin and lib. We store the executable files in bin and the libraries generated in this process in lib. To do that, we will set two variables. One is executable output path, and set this path to project source directory and then bin. Then we also need to set the output path of the libraries and set it to be lib under the project source directory. Now let's see a demo. I have added the two commands into CMake list and also add the two folders. So let's go to CMake and then make. We go to the subdirectory src, and here there is no executable file and libraries because we have reset the path to store them. So we go to bin and lib to see what's there. In bin, we can see the executable file hello, and let's run it. It works fine. Then let's go to lib, and we can see the static library in lib. Sometimes we want to use other libraries in our project. So now let's see how to do that in CMake. We reuse the files in example file, and this time we don't need the hello.c in the source code. Instead, we directly use the libraries generated in example file, and we still need the header file in include. This header file, the libraries, and the main program, and this outer CMake list are the same as example file. We just change the structure and rewrite the inner CMake list. In the previous example, we built a library by add library, but this time we want to use the existing libraries. So we can use link directories to add this given path in which the linker should search for libraries. And here is the lib folder. The linker can go to this folder and find the libraries. We also need to change the second parameter of target link libraries to be the name of the library you want to link. Let me demo it. I have prepared the files and also changed the CMake list to include directories and the static library. So let's go to CMake and then make. Okay, let's go to the bin folder to see the executable file. We can see that it prints hello static libraries because we have linked the static library to it. And it's also very easy to link the dynamic libraries. You can just change the name of the library. We go to the inner CMake and CMake list and change the name of the library to .so. That means the dynamic library. And go back and CMake again. This time we run the executable file and we can see hello shared libraries, which means this executable file is linked with the shared library. Now we know how to use our own libraries, but we also include third-party libraries in our projects. So CMake has support for finding the path to some common third-party libraries. We can use find package and the name of the third party to find a CMake module for this library. Actually, CMake searches for a file called findpackagename.cmake. I'll show it later. Let's see an example using pthread library. In the main program, I create some threads. Here is the inner CMake list. First, I use find package in the module mode to find the module threads, which is predefined by CMake. Parameter of find package is thread. Here we use thread because we want to find a file called findthread.cmake. And this file is prepared by CMake, so we can just use this name thread. The second parameter required means it will stop the process if CMake cannot find the package. And here is thread. Then we add the executable file hello and link the hello with this library. Here the threads threads means the thread library defined in the module find thread. So here find package has two modes. One is module mode and another is config mode. Now we use the module mode, so actually we find the module, and that is find thread. So here the first thread means the module find thread, and the second thread means the thread library. So if you want to use other third-party library, you can search the usage of the library. In the demo, I have prepared the files, and let's have a look at it. First, let's see main.c. I create 5 threads, and each one print a line hello world. Then let's see CMake. First, we find the package thread and then link it to the executable file. Now we go to build and build the project. Okay, and we go to bin to see the executable file. Now we can see the 5 hello world in each line. Remember, in find package, we find the threads in a directory, and that is this directory. Here, the user means where you install the CMake, and for me, it's user. Then is share, CMake version, and modules. Here we can see there are many modules, and what we use is also here. Find thread. Finally, I want to introduce the predefined macros in CMake. In C programs, if we want to print debug message, we often write it in this way. So how to define this macro in CMake so that we can print the debug message? We can use add definitions -d and the name of our macro. So for this example, we can use add definitions -d debugging, and we will define this debugging macro, and it will print this message. Let's see the final demo. This time we have one source file, main.c, and let's see it. Here in main.c, we will print hello if we have defined hello, or it will print bye. So let's write the CMake list. And as usual, we will write some basic commands. Then add the executable file. main.c from. So now we want to define the hello macro in this CMake list. So we use add definitions and -d hello. Okay, and let's go to CMake. No problem, and make. Let's run hello and see what it will print. It's hello. So let's remove the command in the CMake list. If we remove these definitions, let's see what will happen. Clear the folder build and CMake again. Let's run hello. This time it prints bye because we didn't define the hello macro. That's all for this tutorial. Thanks for watching.